Hey guys, and welcome back to reviewing the problems from Biweekly Contest 52. This is the last problem. It is rated hard. It is called Sum of Floored Pairs. And during the contest, I actually had about, I joined a little late, so I had about 50 minutes to try to solve this problem. And I actually thought of a O of n log n, so n times log n solution. But it didn't work. I didn't manage to code it out. There actually is a O of n log n solution, but after the contest, I went and ate breakfast, had a walk, and after I came back, I decided to try and optimize my O of n log n solution by using a hash map, and we will see that later when I explain my solution to the problem. And it actually got accepted, so pretty unfortunate. I could have AC'd this problem, and if I did, I would have solved all 4 problems in the contest, which would have been pretty nice for the rating, but what can you do? So I did not manage to come up with the O of n log n solution and did not solve this problem. But yeah, I'll still go over the solution which I wrote after the contest that did get accepted and show you what I did. So to get started, let's go over what this problem wants us to do. And so it gives us an array of integers, and so if you permute all the possible combinations of two numbers and divide them and take the floor of that, so just regular integer division, and add them all up, that's the answer that you need to return. So if I was a little confusing there, so in their test case, you take 2, you divide that by 5, and you divide that by 9, and then you also take 5, and you also divide that by 9, and divide that by 2, and then with 9, you divide that by 5 and divide that by 2, and that's seen like here, which is 4, 1, 5 divided by 2 is 2. So you also divide it by itself, which is, of course, going to be just 1, and this is going to be 0. So, yeah, I think the problem is not too hard to understand, which is nice, but it is quite tricky to solve. Just looking at it, I pretty much instantly figured out that we have to sort this array, because otherwise it's just going to be a mess. And if we look at the constraints here, the length of this array is 10 to the power of 5. So if we don't sort it, and that way there'll be no real tricks you could use to actually quickly find like all the numbers that are larger or smaller than something, because it's going to be really nice to figure out like, oh, I know that the numbers to the left of 2 are larger than it, which basically helps us out a lot, because one observation is, if we take a number, we only want it to be the like denominator of the division that you do with the numbers to its right. So 5 will be the numerator, 2 will be the denominator, 9 will be the numerator, 2 will be the denominator. And like if you take 5 here, you only want it to be the denominator with 9, because with 2 divided by 5, that's just 0. And since we have to sum them up, it's just pointless adding tons of zeros, right? Like you can add a bajillion zeros and the answer won't increase at all. So it was pretty clear intuitively you have to sort this, and since it's 10 to the 5 and log n sort, it'll run in like perfect amount of time, obviously. So yeah, so you sort this, and Then it's a little trickier to make progress because what I originally thought was during the competition is I noticed this. I thought after the sort, since you know you want to add up 5 divided by 2 and 9 divided by 2, you know you want to add those up, right? So I thought you could do a simple prefix sum, and because 5 over 2 plus 9 over 2, that's the same thing as, so like if you have 5 over 2 and 9 over 2 and you add them, because they're the same denominator, that's the same thing as 14 over 2, right? Because these are the same denominator, so you can just combine them on the top. I don't know why I'm explaining that, it's just anyway, let's just keep on going. So I thought we could do a prefix sum because if we have an array that stores the current sum at each point, so at this point the sum would be 2 and then 7, right? Because 2 plus 5 is 7, and then 2 plus 5 plus 9, the sum of all the numbers up to this point, that would be like sorry, not 2 plus 7 plus 9, 2 plus 5 plus 9, that'd be 16. So then if we want to, we could easily find this number on top here by just taking this prefix sum here and this one here, and then basically subtracting them. So 16 minus 2, that'd be 14. So then we'll know the sum of all the numbers to the right of an element. So I thought this was a promising lead because, well, we want this to be the denominator of each of the numbers on the right and add them up. So I thought, hey, we could just instantly know how much is added up, then we can just divide it and add it to our sum. But this problem is a little tricky because it wants you to floor it. So in this scenario, it's actually 5 divided by 2, which is 2, and then 9 divided by 2, which is 4. So you would not return 7, and you would actually return 6. So yeah, this went out the window. And then so I thought, because this is sorted, we could use a type like a slightly modified binary search, because I've seen a problem like this before where I'll just explain what we're binary searching on. So like we know 2 will go into 9 4 times, right? So we'll know that there are some numbers where in the middle here, like after 2 and between the rest of the array, there are some numbers here which 2 will go into 1 time. There are some numbers which 2 will go into 2 times, and then 3 times, and then 4 times, and then that's it, right? Because it's the largest number, 2 only goes into it 4 times. So then what we essentially can do is we can binary search to find the smallest number which 2 goes into. So that's 2 goes into once. Then we do that for 2, then 3, then 4. And then we also find the largest for all of these. So let me just describe with an example. So if we have 3 here and we're looking for some numbers here, we have some numbers here, right? Like 5, 6, 7, and 8, and yeah. So we can compute what 3 will go into once. The left endpoint of that will be just 3, right? So we'll look for that. And then the right endpoint of that will be 3 plus 3, or yeah, 3 times 2 minus 1, because we subtract 1 here. When we divide by 3, this will essentially get floored. So 5 divided by 3, that's still 1. So what I'm thinking is, if we can binary search and find the right endpoint of this, so like 5, and let's just say we had a 4, if we can find this endpoint here using binary search and this number here using binary search, we'll know how many numbers 3 will go into once. And then that's just a simple matter of taking this right endpoint, subtracting the left endpoint to know how many numbers are in between, and multiplying that by 1. And then we can do the same thing with 2. So we'll try to binary search on the leftmost number that 3 will go into twice, and then the rightmost one. And in this case, we will actually go all the way to 8, because 3 times 3 minus 1 is 8. So when you divide it by 3, 8 will still get floored. But 6 is the smallest number, which will still divide and equal 2. So if we can find this range here, we can just do right minus left times 2 and add that to our answer. And this was what I thought of during the competition, but yeah, it just I didn't know if it would work, and I kind of kicking myself because it does work with one clever optimization. And so that's essentially the algorithm, and I'll go over how that's implemented here. So first, the answer wants you to return it modulo this. So I just have that here, and ignore this map for now. I will explain the purpose of it later. But here is essentially what we do. So yeah, just ignore this map thing here for now. So just look at these two for loops. Okay, so we sort the numbers and we go through all the numbers starting from index of 0 to the end. And so that'll, yeah, go through all of them. And then we divide the last number by the current number. So this is at most how many times you'll go into. Like this number can go into the largest number, right? So then we can loop through from j equals 1 to j equals that. So j will represent how many times our current number can go into another number, right? So like 3 would go into 5 one time, and 3 would go into 6 two times. And so j would represent that. So now we initialize these targets, which we want to binary search on. So the left endpoint will be simply the number multiplied by j, and the right one would be simply the number multiplied by j and then plus this number minus 1, because like we want to find if we want to find all the numbers which divided by 3, let's just use 3 as another example. If we want to find all the numbers divided by 3, and let's just say we want it to floor to 2, we would want to search from 8. We want to search from 6 to 8, because any number in between here, when divided by 3, that'll still floor to 2, right? So that's what these targets are for. And so then we'll binary search for that index. So this Boolean marker here just represents if we're searching for the left target or the right target, because the logic is just slightly different for whichever one you're searching for, right? Because if we find the right target, we want to give the first number that is, want to return the index of like the how to say this. So yeah, let me just give you another example, right? So let's just say 6 doesn't exist. So we have 7, right? With our left endpoint, we would want to find the first number greater than or equal to 6. So we'd move this up 1 to 7. So we would return the index of the 7. But with the right endpoint, we want to find the first number less than or equal to 8. So we'd want to return this minus 1, right? So this marker essentially tells us, hey, do we want to find the right endpoint or the left endpoint? So we know to increment this up 1 or minus 1 if we don't exactly find this exact value. Because remember, our general binary search algorithm, it will see if a number is in a sorted array, but if it's not, it doesn't do anything about giving us, it doesn't give us any information back. But in this case, we want the information of hey, we're looking for 6, but if we can't find 6, we still want to know the index of the first number that's greater than 6, right? And um, another check there would be the first number that's greater than 6, but still less than 8, which is the right endpoint, because then that would be the index out of our left endpoint. So then we can use these left and right endpoints again, which I mentioned earlier, to essentially calculate how many numbers are in here, which all will divide and floor to 2, and then we'll do the same for 3 and 4. So this is just the binary search algorithm modified. So I essentially copy pasted my, well, not copy pasted, but I've written binary search enough times where I can just instantly type it out. So I just typed it out and then made some modifications essentially here. So here is where you regularly find the number. So this is when the number in the middle equals your target, right? So regularly you just return true or like, yeah, this exists in the array, but here I just set both left and right to that target which I'm searching for, and then I look at this flag, and if I'm looking for the left endpoint, I will decrement this while I'm seeing the same number, because there still can be duplicate numbers, right? So if I have tons of 6s, I see, hey, there's a 6, I set my left endpoint there, I want to keep on moving it back while there's still 6s so I can find the right index for my left endpoint. That's a little confusing. Find the correct index for my left endpoint. And so I decrement that, and then after I run into a number like, hey, this is like 5, that's not what we want. We want the index of this 6 here. We will just return left plus 1, and then the reverse logic for the right endpoint. And so that's what happens if we find the number. And if we don't find the number, like, then we know, like, hey, this left guy, he should be pointing to a number that's too large, because we do mid plus 1. So we would still decrement this until we find the first number. Well, not like, we would just decrement this until we find the first number that's greater than our target. So like in this case, left might be pointing to, like, I don't know, 7, and there's some 7s, and then we know, oh, we couldn't find a 6. 6 doesn't exist, because if the 6 existed, we would have found it in this binary search, right? But then we know, like, this is pointing to like a 7, so we want to decrement this until it's not 7. And yeah, so the same logic would apply. It's just that in this case, since our left endpoint is 6 and we didn't find 6, we wouldn't run into this case where we can just set them both to the middle and break out. We would just go all the way. Our binary search would run out, and that's when our left and right would be either on the same one or slightly different ones, and then we know the number's not in there, but we can still use that information to help us, because we know our index should still be roughly in the right place, and we can just move it to where we need to. So this will return the correct index. So in the case of the right target, it'll return the index of the first number, like the rightmost number, which satisfies our right endpoint, and same with the left, which is this. And here I just do a test. If we did find a true like range, so if right's greater than or equal to the left endpoint, then what we can do is we also need to test this, right? Because we need to make sure the left index is less than or equal to the right target, just to make sure we found a valid, like, range, right? Because it's totally possible that there's no numbers in between 6 and 8, and the array looks like, I don't know, 2, 599. We find nothing. We return some nonsense indexes here. So we're just checking here to make sure that, yeah, we did find a real range of numbers that we wanted to find. And so then we perform the calculation in here. So right minus left plus 1 will tell us how many numbers are in this range, because let's just say left points to this guy. Let's just call this index 2 here. And then let's just say, for simplicity's sake, our right points to this guy, which would be index 4. We know there's 3 numbers in here, so that's just 4 minus 2 plus 1, which is 3, because it's inclusive of this endpoint. And we multiply that by j, because j, again, is the number after we divide and floor it. So yeah, because we want to add up all of these divisions. So when we floor it, nums I divided by nums j, we know that's going to be equal to this j right here. So this is the answer. And then yeah, so now I should probably explain what we do with this map, because without this map you actually TLE. So basically this map just saves us some time from having to recompute, because if we look at this example, we find out the answer for 6, right? Like if we divide this by 6, etc., etc., we run to another 6, we know that's just going to be the same answer. So instead of having to do all this binary search and endpoint stuff again, we can just look in our map. So that's why here we have a if this map does not contain nums I, which in our example we're talking about right now would be a 6, then we'd put that, and this thing that it maps to would just be the sum that we would need to add, because that's here. So in this case, if we don't see it, we'd calculate it, we'd put it in, and then here, no matter what, we would add this thing we just calculated to our answer. And so essentially, if we have not seen this number before, we do this calculation, add it to the map, and then look in that map and add it to our answer. And otherwise, we know, hey, I can just look in the map and already add it to my answer. And then at the end, we can just do answer mod, because we want to modulus this. And important that we're using longs here, because then it wouldn't overflow, because it says the answer may be too large. And yeah, whenever it says that, you usually just want to use a long and modulus at the end, and cast it to an int and return that. So yeah, sorry that was a bit of a long explanation, but yeah, the solution should work. Yeah, it's still accepted. It's a little bit slow because there is a O of n log n solution. Yeah, but yeah, that's about it. This is the last problem. I'm a little bit disappointed I didn't write this solution during the contest, because I had quite a lot of time. But yeah, that's about it. Thanks for watching. I'll be back with another video soon.